Hello, I'm Kotsuya Nakamura. I belong to Department of Civil Engineering, Faculty College of Science and Technology, Nihon University. Title of my presentation is Validation of AE-Tomography based on model test of a soil specimen with a heterogeneous elastic wave velocity distribution. This is the contents of my presentation. Introduction. In the study of the progress failure of a solar structure, acoustic emission testing has been applied to the microclock detection using AE source localization techniques. To clear image of AE, example of AE sensor and measured AE is shown below the slide here. Next, the advantages of using AE source localization techniques. First of all, AE measurement is conducted with a sufficiently small time interval. It means details of progress failure. In addition, the measurement is conducted by a lightweight and portable sensor. It means possible of conducted complicated model testing. Objective. Problem of the AE source localization. The source localization on soil specimen of non-uniformity is limitedly performed due to the diffraction and the refraction of elastic wave. Approach of solving a problem. AE tomography has performed on identification, elastic wave velocity distribution, and localizing AE sources with a constellation of the diffraction and refraction of elastic wave. Objective. In order to discover the potentiality of AET on soil specimen with a heterogeneous elastic wave velocity distribution, the author validated the proposed method using a numerical test and model test. Method. This slide is a show overview. AET separated step 1 to step 3. Step 1. In order to consider diffraction and refraction of elastic wave, ray tracing is applied to AET. Ray tracing is a way to overcome the diffraction and refraction of elastic wave by estimating the minimum travel time. Minimum travel time from AE sensor to candidate over AE sources is estimated by velocity distribution on each cell. Each cell has a different velocity, so minimum travel time over the target could simulate the diffraction and refraction of elastic wave on the target. Where first step is calculated hypothetical velocity distribution is located into the cell before starting analysis. Hypothetical velocity is located highest one in the possibility. After that, candidates over pulse originated time are obtained from equation 1. It means that the candidate over its estimated each point. Number of candidate each point is the same as a number of AE sensor. Step 2. AE source is defined by a minimum variance of candidate time plus original time as the average of candidates on defined point. Measured travel time is obtained from equation 2. Step 3. Velocity distribution is updated by one of the inverse analysis, SIRT, using your difference between your measured travel time and estimated travel time. From step 1 to step 3 is iterated until convergence of the source localization. Minimizing mesh dependency. Accuracy of AE sources localization is related with mesh size. If cross of a mesh has defined candidate points. However, shrinking mesh size lead to increase in calculation cost as exponential. In this paper, Lagrange interpolation is applied to AE source localization, minimizing method dependency. Interpolating function is here. This is and also this is an overview over a source localization by interpolating function. This function is defined by various of originated time and coordinated over candidate point, and could describe the point smallest various of it. It could be differentiated by coordinated over source point. So AE source in cell is allocated point differentiated function equal to 0. Numerical test. AET is applied to heterogeneous elastic wave velocity distribution to validate the performance of overcoming the diffraction and refraction over elastic wave. Input data is arrival time estimated by event located randomly on exact velocity distribution. According to the initial condition, initial velocity distribution over case 1 is the same as the exact velocity distribution to validate the performance of Lagrange interpolation. Initial velocity distribution over case 2 is the same as the upper limited, and upper limited is the highest velocity in exact one. So case 2 is to validate performance of identification velocity distribution and a source localization in a favorable condition. Results. According to the results over case 1 and case 2, error over AE source localization are smaller than size of the mesh. This shows that Lagrange interpretation work well, minimizing mesh dependency. According to the result of case 2, physical boundaries are identified approximately. Iteration over identified velocity distribution only work on a cell on cell where wave gets through. If the number of events is increasing, the cell where wave gets through is increasing, and it is expected to be clear the boundaries. Rather than case 2. Conclusion. The authors validate AET using numerical tests to discover the potentiality of AET on soil specimen with a heterogeneous elastic wave velocity distribution. The results of all cases show that Lagrange interpretation work well, minimizing mesh dependency. And physical boundaries are identified approximately on case 2. Prospects for the future. Validation of AET will be conducted by a model test to show working with actual measurement value. And in order to conduct validation of AET by the model test, A generated artificially will be measured by a 6-channel over AE sensors valid in a solid specimen. These are tested, and results will be detailed in this paper. Thank you for attention.